Calculus! This is AP Calculus Lesson 5-6, Analytic Definite Integrals. I would be coming to school, but I caught Riley's stomach virus and I feel horrible. So I am staying home today so you guys also don't catch this and feel horrible. Let's talk about analytic definite integrals in terms of types. So we know indefinite integrals. We've been playing with them all of Lesson 5 so far. So these are also known as, so aka indefinite integrals are also called antiderivatives. I've been using that word interchangeably, antiderivatives. And when I say indefinite, what I'm really saying is that we don't really know where the start and end value is. You're just assuming that you're taking all of the function. So this means that we don't know where the start and end is, and that's kind of the keywords here. You might think that's dumb, but those are keywords. Start, got some lag, start, and end. Come on now, and end are. Oops, R is not a keyword. All right, so what does this look like symbolically? So we'll have some integral like this, and we'll say some f of, I don't know why so much like f of x dx. And when we evaluate this, this is just the general antiderivative. Do you guys remember what this turns into? Go ahead and think about what it is now. If you know it, go ahead and write it. Pause me if you need to. But this guy is capital F of x plus c. So whenever you take the antiderivative of lowercase f, you get capital F. It's just one of our definitions. We've seen this before, and this is just all review. This is our new stuff. The definite integral. So this normally throughout all the world is just called the integral. So this is the integral. So I'll try to use antiderivatives more when I'm only talking about something that doesn't have start and end values, and integral more when we actually have start and end values, now that we have a formal definition, well, at least semi-formal definition. So definite. Definite means that we do know where the start and end are. So we do know. I'm just going to say start and end. Start and end. Come on now. And end values. So what does this look like? Symbolically, we have the integral, and now you can say the start and end. We'll just say a and b. You can put a here, you can put a here. It doesn't matter, somewhere in this vicinity. If you're trying to save space, you want to put a here. If you are being very fancy, you'll put a there. I'm being fancy, I have a lot of room here, so I'm going to put a on the top and the bottom, a and b. All right, so these, I guess I should finish writing my inequality before I start talking about it, and then we'll have general f of x dx. All right, so this thing has a start value of a. The start value is always on the bottom, so start is always on the bottom. That end value is always on the top. That will never change. Start is always a, end is always b. All right, so this doesn't just turn into f of x plus c. It's something a little bit more specific. So what I do is I evaluate capital F of x. So this now turns into capital F of x. And no plus c. You no longer have a constant of integration for definite integrals. You are now evaluating what this interval is. The way you do that is writing an evaluation bar. So it's just a giant bar, kind of looks like half of an absolute value sign. And you say, okay, I'm going to plug in from B to A. That's how you write that. I'm evaluating from B to A. And what does this, how do I actually calculate that? Well, you just plug in B and then you subtract. So this is capital F of B. I plug in B and then I subtract the start value. So subtract the start value, which is F of A. And that is a formula. I guess I should have put a star here. I'll do it informally right now. Can you put a star here too? This is our key formula. You'll be using this over and over throughout today's lesson and assignment. All right, so the procedure, I mean, I already kind of walked through the procedure informally up here, but the first step is to do like we always do and take the antiderivative. Antiderivative. And then you need to plug in your values of your end value and then your start value. It's kind of backwards, right? You normally think you plug in your start value and then your end value, but you plug in your end value and start value. So I'm going to say plug in end and start value. And once you plug them in, you just need to subtract them and you're good. So subtract. And you will get hopefully a number out of this. If they gave you a number, maybe it'll be kept general like this. It depends on the problem. So let's see an example. We have example 1 on the front, 2 on the back, and then talking about why the constant of integration disappears. So example 1. Here is the definite integral from 1 to 3, that's how I pronounce this, the definite integral from 1 to 3 of 3x squared dx. Okay, so this is simple powerhouse. So you know how to take the antiderivative. So go ahead and take the antiderivative now. This is going to be equal to what? And then I know some antiderivative there, and then it's going to be an evaluation bar from 1 to 3. All right, so you already found the antiderivative. It should be 3x to the power of 3 divided by 3, which is the same thing as x to the power of 3. Okay, well now I need to plug in the end and start value. Let's change colors here. So when I plug in the end and start value, I have x to the power of 3, and then I'm going to subtract the start value to the power of 3. So my values for my end was 3, my start was 1, and now this comes down here, and that evaluates as 3 to the power of 3 is 27. It's 3 times 3 is 9, 9 times 3 again is 27, minus 1 cubed minus 1, and that finally turns into 26. All right, so there's our procedure. Let's go ahead and look at another example. All right, so we have this example. Be careful on this one. Always, every single time that you're looking for an integral or antiderivative, general or definite, or sorry, indefinite or definite, always be checking dinner. What is dinner here? Okay, you should be answering, but I'll help you if you can't find it out. So inner is 3x, so the derivative of the inner, the dinner, is 3. Whenever the dinner is not equal to 1, you always have to use U substitution or taxman. I'm just going to use taxman to get through this nice and quick. So my U is 3x, my taxman is 6, he's knocking on the front door on E house, and then U prime, the derivative of U, is 3, which means I'm going to pay the taxman with 2. Alright, so I'm going to rewrite this integral, okay. I have to be careful about this. So using taxman, these bounds don't change because taxman is a cutesy little trick, but using U substitution, these bounds do change, and I'll be talking about that in a sec. Maybe I should keep this side for taxman and this side for U substitution, because it is important to know both ways. They do vary now. So this is now the integral, and let me move these equal signs. I need to conserve space here. This is equal to the integral, the definite integral between 2 and 3 of 2, I paid the taxman, 2e to the 3x dx. And then from there, I guess I'm just going to come down here. I should just start down here, I think. When I take the antiderivative, e house stays the same, so my antiderivative is 2e to the 3x, and that is going to be evaluation bar between 2 and 3. So what is that thing equal to? This thing is, I'm going to plug in 3 first, so this is going to be 3 to the power of, or 3 times 3 here is 9, so it's going to be 2e to the 9 minus, and then 2e to the 6. 2e to the 6. And there's our final answer. So we can do I have technology for a perfect box. There's our final answer. Did I back my last question? I did. Alright, so let's look at what happens with U substitution. There's a tricky little thing that happens that you might not think is important, and I didn't either when I first saw it, but there's going to be at least one question on the AP exam where they ask this question, maybe even 2. Alright, so let's do U substitution. We know we need U, which is going to be 3x, and we know that we need du dx. du dx obviously is 3, and therefore we're going to solve for dx, which is 1/3 du. So when I change everything for u substitution, since this is our formal way of doing it, u substitution is like the same throughout the world. If you go to China or India or wherever, they're going to be using u substitution. So to stay formal about this, this is no longer evaluated between 2 and 3. And you need to ask yourself the question, why? And I'm going to come back to that. Give yourself about that much room, because we're going to be writing more than just numbers here. When I use u substitution, then this is going to be 6e to the power of u, and then this dx is now going to change into 1/3 du. 1/3 du. Okay, so that question I'm going to answer now. What this integral, this definite integral, was saying was evaluate between x equals 2 and x equals 3. This right here is really a shortcut for saying evaluate between x equals 2 and x equals 3. I mean, you just assume that the numbers are x because that's an x, that's an x, nothing else is a y. So how do we change that? I mean, right now everything is in terms of u, so if I put 2 and 3, I can put x equals 2 and x equals 3, but that's not going to help you on the multiple choice question. The multiple choice question will say between u equals what and u equals what. I need to change the bounds in terms of this u substitution over here. But look at this. We have this handy-dandy equation, u equals 3x. So I can find the value of u. Well, if it was 2, plug 2 in for value of x, because that was x. 2 times 3 is 6, which means this u value is 6. And if I plug in 3, 3 times 3 is 9, the u value is 9. So by changing the bounds, this is now formal u substitution with the definite integral. Okay, so now I'm going to take the antiderivative. My antiderivative is going to be, well, this simplifies to 2 because 6 divided by 3. So my antiderivative is 2e, come on now, e to the u, evaluation bar between 6 and 9. So the cool thing about u substitution when you change the bounds like this is you don't actually have to switch the u back to x. Look what happens. I can just plug in 9 and 6 because those are values of u. I can plug them in directly right now. And if I do that, I get the following answer. 2e to the u, I'm going to plug in my n value first, to the 9 minus 2e to the other start value, which is 6, which is the exact same answer that we got over here. Alternatively, you could change this u, and this u all back to x's, which means you have to undo changing this 9 and 6 and make it go back to 2 and 3. Alright, so that is a little bit confusing. It is worth 1 point on the AP exam. It is worth memorizing and understanding. And if you don't understand, you can ask me when I'm back to school. Alright, I know we already have a long lesson compared to normal, so let's go ahead and get through this. What happened to that constant of integration? What happened to that plus c? Where'd it go, Mr. Sandell? You said it's gone, but prove it to us. Alright, I'll prove it to you now. So this guy, by our definition, by our starred definition up here, this thing is going to be equal to, I'm going to take away one of the derivatives, one of the primes. So this is going to be f prime evaluated, or f prime of x, I should say, to keep it formal. F prime of x evaluation bar is evaluated between 1 and 2, which is the same thing as f prime of 2 minus f prime of 3, or f prime of 1. I don't know what I'm saying here. All right, and that would be our final answer. You're asking, okay, well, where can you just say like plus c there? And the answer is no, and I'll show you why. Let's go ahead and do this problem a little bit more formally. And by that I mean let's just go ahead and add the c. So let's change this to f prime of x plus c. Boom, there it is. We have the c in there, right? And that's evaluated between 1 and 2 still. So what happens if we keep the c in there? Well, I have this whole thing is evaluated between 2, or 1 and 2. I was going backwards there for a sec. So that means that I'm going to come down here to the next line. That thing is equal to f prime of x, sorry, f prime of 2. What am I saying here? F prime of 2, I'm plugging that 2 in, plus c. That's the first part. Subtract, and then here's my second part. F prime of 1 plus c. Okay, we'll now distribute this negative, and this turns into the next line, which is f prime of 2 plus c, drop the parentheses, minus f prime of 1, distributing the negative, minus c. Oh, look at that. The c there and c there cancel each other out. You're just left with f prime of 2 minus f prime of 1, which is exactly what we got up here, which is the definition that I was giving you up here. So that's what happened to our constant of integration. All right, that concludes the notes. Go ahead and write your summaries now, and then hopefully the substitute has the worksheets for you, and if not, they are on Google Classroom. Good luck.